The kinematic formulas. I remember learning them in school, but I was always left wondering, where do they come from? And why do they only work if acceleration is constant? Let's find out together using some graphs and animations. To understand the kinematic formulas step by step, we'll animate these four graphs you see at the top of the screen, one at a time, starting with the displacement versus time graph. Don't worry if the other graphs look unfamiliar, I'll explain each of them as we go. We'll track everything in the context of this blue square moving along the number line over a span of 5 seconds. That's what you see at the bottom of your screen. Let's start the animation. On the displacement versus time graph, the x-axis shows time in seconds, and the y-axis shows displacement. Now, displacement simply means how far the object is from a chosen reference point, and in which direction. For example, here, the blue square is 1 unit to the right of the reference 0, and it's stayed there for 5 seconds. That's why in this baseline case, the square stays at that 1 unit displacement for the whole 5 seconds, which is reflected by this flat horizontal line. Meanwhile, the velocity, acceleration, and jerk versus time graphs all remain at 0. That's because the block is not in motion. It's perfectly still. Now, let's examine the second graph, velocity versus time. Again, the x-axis shows time in seconds, but this time the y-axis shows velocity. Velocity simply means the rate of change of displacement, or how quickly the square's position changes over time. Let's start the animation again. In this case, the blue square moves at a constant velocity of 2 units per second over 5 seconds. Notice how this appears on the velocity versus time graph as a straight horizontal line at 2 units per second. Meanwhile, the displacement versus time graph now shows a straight rising line. That's because displacement is changing over time. The square is getting further and further away from the reference point at a steady rate. In other words, the slope of the line is the velocity. This leads us to our first basic formula. Velocity is the change in displacement divided by the change in time, the rise over run on the displacement time graph. Also, we can calculate displacement directly from the velocity versus time graph. Because the velocity is constant, the graph forms a rectangle. The area of this rectangle gives the total displacement. This leads us to another fundamental formula. Displacement equals velocity multiplied by time. Keep these concepts in mind because we'll use similar concepts to derive the kinematic formulas next. Now let's examine the third graph, acceleration versus time. As always, the x-axis shows time in seconds, but now the y-axis shows acceleration. Acceleration is simply the rate of change of velocity, how quickly an object speeds up or slows down. Let's start the animation again. This time, the blue square moves with a constant acceleration over 5 seconds. To set the stage, let's assume that before it starts accelerating, the square is already traveling at 1 unit per second with a constant velocity, and then begins accelerating shortly after. Notice what happens in the graphs. On the displacement versus time graph, the line curves upward. On the velocity versus time graph, we now get a straight rising line. From here, we can begin to derive the kinematic equations. First, the slope of the velocity time graph gives us the acceleration. Rearranging this relationship gives our first kinematic equation. Final velocity equals initial velocity plus acceleration times time. Second, just like before, the area under the velocity time graph gives us the displacement. Because the acceleration is constant, this area breaks nicely into a rectangle and a triangle. That's why we can compute it directly. Remember this point, as it will be important when we look at why acceleration must be constant for this to work. Ultimately, this gives us our second kinematic equation. Displacement equals any initial displacement plus the area under the velocity line. And finally, the other two kinematic equations can be obtained by manipulating these first two formulas. And there you have it, our 4 kinematic equations. But we still have to answer the question, why do these only work with constant acceleration? To understand why the kinematic formulas only work with constant acceleration, let's see what happens when acceleration is not constant. For this, we introduce the jerk versus time graph. As usual, the x-axis shows time in seconds, but now the y-axis shows jerk. Jerk is simply the rate of change of acceleration, how quickly the acceleration itself is increasing or decreasing. Let's start the animation with some jerk added. This means that instead of staying flat, the acceleration graph is now a slanted line, gradually increasing over time. Notice the effect on the velocity versus time graph. The straight line has become a curve, and on the displacement versus time graph, the curve is even sharper, bending upward. This curved line in the velocity versus time graph is the key problem. Our first kinematic equation came from the fact that velocity increased with a straight line, but with jerk, that line is curved, so the formula no longer holds. Our second equation came from neatly splitting the area under the velocity graph into a triangle and rectangle. But again, with a curved line, those shapes don't exist anymore. So, if the first two equations break down, then the third and fourth equations, which depend on them, also fall apart. This is why the kinematic formulas only work when acceleration is constant. Now you may be wondering, can we still calculate velocity and displacement when acceleration is not constant? And the answer is yes, we can, but we need calculus to do it. That, however, is a story for another video.